something you have to go through in order to do something else in life. Why is it that they who come trailing clouds of glory, for whom triangles are platonic and not pathetic, why do they lose that sense of wonder, of awe, curiosity, imagination, and find that this art is slavery, when mathematics is freedom? Everything that Mark said, I think, just hit the nail on the head. Mathematics is freedom, and the point of math circles is to restore this dreadful imbalance between the beauty of math and the way it's been forced on people in an authoritarian way so that it's cookbook, it's recipe, instead of glory. Our approach is to work always collegially, always cooperatively, never competitively. Why not appeal to the best in people? And perhaps Ellen and I, unlike almost everyone in this room, think that there's no such thing as talent in math, that this is a myth and a pernicious myth. Everyone can do mathematics creatively, not just absorb it, but actually create it, if teased along in the right way, if encouraged, if allowed to take charge of their own lives, of their own thoughts. So that what we try to do in the math circle, and you'll see this morning, I hope, who knows, it might be a complete disaster. That's part of the fun of it, that it's a high wire act. You don't know what's going to happen. What we try to do is pose an accessible mystery, something which is attractive to them, which they hadn't thought about, and which you think they might be able to get a handle on. We, leading the class, know where we want to go, but it may not be at all where we're going to go. Follow their leads, a point that Mark made. This is an interaction between you as a person, with them as people, individuals, with their insights and their blind spots. And you want to be able to look at them and have them look at you and work collegially together. Let me give you an example. With the 4 and 5-year-olds that I'm working with this year, our math circle is in Cambridge. Quick background, we began in 1994 with 29 students. We now have, we average about 110 each semester, going in age from 4 to adult, meeting in groups of, well, Mark said 8 or 9 is a good number to work with. 15 would be a maximum for us. There have to be enough to have a diversity of points of view, but not so many that each person can't hear him or herself talking, thinking. Pose a question. The question I posed to my 4-year-olds at the beginning of this semester, the semester is 10 one-hour classes over the 6 months. The question was, what's the area of a circle? In other words, I walked in that first day and said, hi, my name is Bob, what's the area of a circle? And one of them said, what's a circle? And I said, I have no idea. And a girl sitting over here said, well, it's, you know, it's every which, you know, it's round. And I said, oh, right, you mean like that? And a little boy said, no, she said round. Oh, I said, sorry, you mean, no. Eventually, they get to see you as their nice but slightly dumb friend at the board, and they can teach you things, and that's perfect. They're in charge. After about 10 minutes, a girl who hadn't said anything up to that point said, you know, it's when you're standing in the middle and every which way is the same. Wow, pretty good. So we had a definition of a circle. We had 3-step circles, i.e. the radius is 3, and so on. I said, oh, great, okay, so what's this area? Someone said, what's area? I said, I have no idea. And we were off onto the next hour, the week later. And they came through conversation, listening to one another. Amazingly enough, at that age, they do listen to one another and saying, well, you want to pour cornflakes into it and spread them out. I said, oh, that sounds terrific. You mean, and yes, and see how many you have. I said, great. Someone else said, can't do cornflakes. Why? They're not all the same. Well, they're all cornflakes. No, I mean the same, you know, thing. What do you mean thing? get them to understand what it means to define. They've got to be all the same shape-ish. Well, shape-ish, good. We ended up, I'm condensing into 1 minute what took over an hour. We ended up with squares poured in every which way, some sticking up out of the circle. And then, no, they should all be the same size, they should all be flat. Problem, some of them are sticking out of the circle, and some of them aren't quite getting up to its edge. After 10 hours, we got that the area of a 3-step circle was more or less 29, kind of between 27 and 31. They left in exhilaration and exhaustion, as I did, knowing that they'd gotten a huge amount, but they hadn't gotten it quite right. How on earth were you going to deal with the gaps? Someone said, as we left that last day, someone said, why don't you slice some of those squares in half and patch with triangles? Oh, that's going to be the way to do it. Goodbye. And that's a real, from our standpoint, that's a real math circle, because you've made a huge dent in the problem. You've learned something about mathematical thinking. Your personality has become involved with the problem, with the personalities of others in the room and with mine. And the whole process has moved forward on many different levels, social as well as mathematical. What's going to happen today? Well, who knows what's going to happen today? We're going to have 9, I think, experts coming in. It could be disastrous. A point that Mark made about these rules, a good friend of ours, a Montessori teacher, said when you're talking to kids, I think it applies when you're talking to one another, treat them as friends, as adults, talk to them as adults, but when you see the eyes glaze, stop dead in the middle of a sentence, because you're not going to get any farther. When that happens, what we tend to do is play these what we call function machines. Someone makes up a rule, other people try to guess what the rule is by giving inputs and seeing what the outputs are. If someone says, oh, I see what the rule is, we say, well, hold on, as you said, Mark, join us and give an input. Make guesses. Everyone make guesses about what the possible function could be. Hi! Samantha. Hi. Hello, Aaron. Hi, Nico. You
So you guys get to sit in the chairs, right?
Yes, you can actually be in the chairs. They are yours.
Here we go. Say, Nico, come on over here. I'm going to make some space for the floor.
Aaron?
Right here.
Louisa, where would you like to be?
Next to Nathan, thank you.
Reed, do you want to be over there? I think we're great. Hi, my name is Bob, and what I was thinking about on the way over here was this: how big is big? How big is big?
Very big.
Very big. Well, how big is very big?
Very, very, very big.
Well, give me an example.
Like a truck is big.
A truck?
A truck.
A truck is big, you're right. Anybody have another example of how big is big? How big is big, Samantha? Give me a number. Yes, Louisa.
This tall.
That tall. How tall is that roughly? Is that about 5 feet tall?
No.
How tall? 2. So 2 is big. 2 is pretty big. Certainly bigger than 1. Anybody have something, Nico, bigger than 2? Yeah, give me something bigger than 2. How big is that?
10,000.
10,000. Wow, that's wonderful. Wait, let me just write that down. We've got 2. We've got 10,000. Is 10,000 bigger than 2?
Yes.
How do you know?
Because it's way bigger.
It's way bigger.
And it's also bigger than 100.
You're right, I think. Is that right?
Yeah. Yeah, 900.
Okay, wow, wait a minute. 100, 900. I think that is probably the biggest number there is.
No.
No.
A million. A million.
I've forgotten a million. I think you write it this way, a million? Maybe, I'm not sure. I'll call it a million. Well, that's the last number, right? That's the biggest number there is.
No.
Why not, Ben?
1,000 million billion.
1,000 million billion. How much?
A trillion.
How do you know these numbers? A trillion, 1,000 million billion. Fantastic.
5,900.
5,900. These are
Not the
giant.
biggest number.
That might be the
There's
biggest
bigger
number.
numbers.
There are bigger numbers? How do you know?
10,900.
And maybe that's the biggest.
No, the numbers just keep going on and on.
Really?
No, numbers can stop. No, 10 plus 10 is.
What?
I know 5 plus 5 is 10.
5 plus 5 is 10, right.
And 10 plus 10 is 20.
You are experts. I told people experts would be coming in. I was
1 plus
right.
1 is 2.
Wow!
And 3 plus 3 is 6.
Fantastic. But we have two different opinions here. You say, Reed, that there's no last number. And Nathan, was it you who said that there is a last number? Well, maybe you're both right? Can there?
Here's the last number.
What is the last number?
Infinity. That's the biggest number.
That's the biggest number there is, right? Is it bigger than infinity minus 1?
No. No, there's infinity minus 1 is a Google.
Infinity minus 1 is
It's a
Googleplex.
Yeah, and then before that is a Google.
Gosh. What if someone were to walk in right now and say, I'm thinking of the last number of all, the very last, I'm not going to tell it to you, but I'm thinking about it. How could you prove to that person that he or she was wrong? That they weren't thinking of the very last number? That maybe a Google or a Googleplex isn't the last number. How could you prove that? What a strange question. I'm going to change the question. I think 23 is the last number.
No.
Why not?
There's 49.
How do you know 49 is bigger than 23?
Because 3 is bigger than 2 and 4 is bigger than 2, which means that 40 must be bigger than 20 and 40 must be bigger than 29.
That's a nice way of putting it, Nathan. Do you get what Nathan's saying?
And 39.
Right. So if someone says 23, if I say 23 is the last number, you say no, 49 is bigger because the 4 is bigger than the 2. That was the 23 that I thought was last. And the 49 that you say is bigger, 4 is bigger than 2. Is that right? Is that what you're saying? Okay. Well, okay. I'm not going to tell you what number I think is the last one. I'm going to call it, what shall I call the last one? Just give it a name. Don't give it a number name, give it a funny name. Give it a name, Jasper. What, Dada? Dada. Dada is the last number of all. Prove to me that Dada is not the last number.
Not the last number. It's not even, it's a word. I tell you, a number. Infinity is the last number.
Okay, great. Nathan says Dada isn't even a number, it's a word. And you say that infinity, forget all this Dada stuff, is the biggest number. Maybe you're right, but I think Dada is standing for a number in a box. It's hiding in here. The name on the box is Dada. And we don't know what's in the box, but even if we don't know it, you can prove to me and to each other that there's a number bigger than Dada. Maybe just a little bit bigger.
I know.
What?
This is the first number, 0. That's the first number, 0.
Whoa.
No, there's negatives.
Oh,
We have -1, -2, -3, -4, -5.
I said they become trailing clouds of glory. Well, okay, so the 0 is the first number. I'm going to get rid of all these wonderful ideas. They're in my mind, but they're not on the board anymore. There's 0.
Of course they are, just you erase them.
You're right. They're hiding behind here. There are the numbers that go off that way. There are the numbers that go off this way.
No.
What's the first number here?
0.
And then
And then 1.
1. And then,
2.
and then,
3.
and then eventually
4.
dada.
5.
Why not? Why not? Why isn't that the very last one? The name of the
That's
drink.
a number.
It's
I mean a word.
it's a word. Well, Nathan is a person sitting in that chair, but his name is Nathan. Nathan stands for the person sitting.
No, it's a word, not a number. Okay. And
Well-
you're being kind of funny here. Well, Dada
Yes.
is dad.
Yes.
So it's kind of confusing. So it's like you have dad. It's
Yes.
like you're saying dad.
It is. It's like you're saying dad. I thought Jasper's choice was a very good one for dada, but it's hiding behind it. Behind it is hiding the name of the very last number of all, unless there is no last number of all. Unless you can show this.
Here's the
Nico.
last number of 4.
Say that again? What?
4 is after 3.
You're right. Do you want here? Let me write that down here. 1, 2, 3. You want to write it down, Nico? 4. 4 is the number after 3. I understand. You know, you are a much better writer than I am. I think I'm going to ask you to do all the writing for me from now on. I put data after 3. What I meant, what I should have said was, there's lots of stuff here, like 4 and other things, and then finally, at the very end, you get data, period. Last number.
No, it's not. It's a word. Not a number.
Okay, let me ask you this. What's the,
5 is after 4.
you're right, 5 is after 4, and then 6 is after 5, and so on. And you go
7
on like
is
this,
after 6.
and then you stop dead, finally. Then you just have used up all the numbers, right? What's the biggest number you've ever seen? Of any,
The
of,
biggest number is infinity.
yeah, have you ever seen infinity people in a room?
Yeah.
Have you? Samantha, what's the most number of things you've ever seen?
There's like 10,000 people.
Wait a second, Nico.
I don't know.
Okay, have you ever seen 9 people all together?
No, there's even more people.
You're right. In this room, I think there are maybe more than 9. 1, 2. Could you help me count? 1,
2,
2.
4, 6, 8, 7, 8, 9.
2, 4, 6, 8, 9.
But there's
Okay.
more there.
I think you're right about the
There's way
9.
more out there.
There are
And
way
then
more out
10,
there.
And then there's more.
Well, how many? How many all together?
I don't know.
Take a wild guess.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14,
Nico,
15,
instead of,
16, 18, 19,
it's going to take a long time to do that. Make a guess. Make a guess. Everybody, make a guess. About
24.
24?
24. 24.
We have all seen at least 24 things. The things happen to be people. But 24 is a pretty big number.
I mean 25, 26, 27. 27, I'll take a guess. 27.
27 is how many people there are in this room altogether. Maybe, but fewer than data, I guess.
Dada is not a number.
Okay, then let me ask you this. What's the smallest? How small is small?
0
0 is awfully small.
is not the smallest number.
Well, what is the smallest number?
Me and my bag. Negative. Thank you.
Negative. Negatives are even smaller than 0. They certainly go on that way. If you are going to have a party with some friends over, Lucia, how many friends would you like to have to your party?
100 million billion. Not really.
That's wonderful.
Not really. But that's really more than that number.
How many? 6 what? 6? A trillion. A trillion friends. I would.
A zillion, that's how I say it.
Okay,
So
that's a very nice idea. You obviously have a lot of friends. But what if you had to get a cake for them and you'd have to have a lot of cake or a very big cake? Could you have a smaller group of just very close friends? Reed, how many friends would you like to have over?
5 is the last number.
Okay, 5 is the last number. Nathan, I think you may be right. I'm going to think about that.
That's because I'm 5 years old.
Oh, you're 5.
Yeah.
Today, is your birthday today?
Yes,
Okay, wait a second, Nika.
I'm 5.
Are you exactly 5 today?
Yeah.
And when was your birthday?
November 17th.
And have you been exactly 5 ever since November 17th?
April. I turn a different number April 17th.
You turn a different number every November 17th. So,
And this year, when it's November 17th, I'm going to turn 6.
and in between,
That's a tall number.
in between the last, Aaron, have a seat again. In between being 5,
Have a seat.
Nathan, in between being 5 on November 17th last year and being 6 on November 17th this year, do you stay absolutely steadily 5 the whole time?
Yes.
Everybody agree?
No, 5 and a half, 5 and a quarter.
5 and a
5
half.
90 quarters.
Oh, I'd forgotten about that. You're saying,
No, it's not open. Because he thinks funny. And I used to say, ow, 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 why you going?
tell me if this is right. Nathan's saying between being 5 and 6, he is at some point 5. How do you write 5 and a half?
And 3 quarters. Okay.
Let's do the half first. 3 quarters is interesting.
5 and a half. Oh. And then like a C.
Okay, a C.
And then I and then
Good,
a diagonal line, and then a 1. Just what you did.
Oh.
Right there.
Okay, great. Have a seat again. Nico suggests 5C. Nathan suggests 5, a diagonal line with a 1
I
over
said 2 and a diagonal line 1.
like that?
Yeah.
Okay, is that
Except without the 5.
without the 5? Right. So in between, you know what? My picture is so messy. I'm just going to blow up that little area. There's 0, there's 1, and in between them is 2 with a diagonal line and then 1. Like that?
Yeah.
Is that okay? Samantha, is that okay?
Yeah, that's okay. That's
Okay.
okay. That's okay.
Ben, is that all right? For 1/2? Midway between 0 and 1? Okay. Is there anything between... Yeah, Nico.
There's something between 9 and 6. 7 and 8.
Good. Between 9 and 6, there's 7 and 8. You're right. Between 9 and 6, there's 7 and 8. Between 1/2 and 1, Jasper, is there anything between 1/2 and 1?
1 is 1 and a quarter.
Is 1 and a quarter.
I mean 0 and a quarter.
0 and a quarter. Okay. Have a seat again. So you're saying between 1/2 and 1, you're... Could this make sense that there's something between 1/2 and 1 and kind of a getting older from 5.5 to 6? That there's something in here? I'm not sure. Ben, do you think that there's something between 1/2 and 1? I don't know. I'm confused.
3 quarters.
3 quarters? Wow. Let me make sure I understand you. Watch, everybody. We're going to make a birthday cake, okay? Here's the cake. Oh, what kind of cake should it be? What kind?
We can't make a birthday cake.
You're going to have a cake for you and a friend. How do you divide the cake so you and your friend have equal shares of it? Half. You like that? What's wrong with that? There are 2 parts.
It's too small.
Oh, you're right. It's not fair. Your friend gets this part and you get that part, right? All right, let's make it fair. How do you make it fair to divide the cake in 2 equal parts?
You just like line it across that can.
Sorry, say it again, Reed.
You just like line it across that middle can.
A line, hey, we have a wonderful idea here. Lucia, we have an idea here from Reed about how to make the cake into 2 equal parts. Is it like this, Reed? Like that? Great. Could you make the cake into 4 equal parts? Anyone?
Then you just brought 2 more.
2 more. Samantha, what does he mean?
No.
I don't know either. Jasper, can you make this cake into 4 equal parts? It's in 2 equal parts now. Don't know. I need your help. I need your help. How can we make the cake into 4 equal parts? We've got it in 2 equal parts. Maybe it can't be done.
I could do it.
Great. Lucia's idea, come up and do that. Just the right idea. Terrific. And in fact, better than what I did because you went right through the middle and my dot for the middle was off. 4 equal parts. How many parts do you want to divide it into now? How many, Nico?
What?
How many parts? We've got the cake divided into, we first did a half, and then we split that into fourths. How many parts would you like to divide it into now? An equal number of parts. Oh, you want 9 equal parts. Let's work our way toward that. Is 9 going to be easy or hard?
Easy.
Easy. What's your idea, Lucy? How do we make 9 equal parts? Do that again. Okay, come up and do it. I think that sounds very good. Good. Terrific. That's a really nice way of thinking. And now we've got 9 equal parts, right? Yes? Nathan, I don't think you can see from over there. I need to.
Pizza.
It's a pizza instead of a cake. We've got 9 equal parts of it, right? Right?
No.
No? Why not?
There's only 6 parts. There's only 6 parts.
Oh, I thought there were 9. There are only 6 parts. Right? There's 6 parts?
Yeah, there's 6 parts.
Reed is counting.
I know what to do.
That's an idea. Hold on to that one for a second. How many parts, Reed?
Well, I counted and it said like 10.
How much did it come out to?
For me, it went like 10.
Okay. We think I thought there were 9. The suggestion is there might be 6 or there might be 10. I think we actually better do some.
8.
8? Is one of these ideas right?
5.
5.
5.
Okay. How do we figure?
Count them.
Count them. Okay. Ladies and gentlemen, the suggestion is that we figure out which, if any of these is right, by actually counting. Jasper, where shall I start counting? There. Okay. We'll call that number 1. Samantha, which way should we count? That way or that way? Good. We're going to count the way a clock goes. Could you all count aloud with me? Can you, Aaron, can you see from there? That's the second piece? Okay, count out loud with me. We're gonna get 5, right? Right?
No, 6.
6, we're gonna get 6, okay. Count out loud with me, what's this one?
3, 4, 5, 6.
Oh, 5 is gone. Oh, 7.
8.
It was 8. It was 8.
Now extra 8.
Look,
We only need 1 more piece.
if we wanted to get 9 pieces, we'd need 1 more piece. How can we do that? To make them all the same size?
10. I know how to do it.
Good. Do you want a new pizza to work on? Here, I'll draw you a new pizza. Okay.
So you got this, huh?
Yep. Yep.
This is next to the 7.
Right. That's the next after 7.
And then after is this double.
Yep.
And then after that double, it's 11.
After that one's
Got
20.
2 and 1.
Okay. So we know how the numbers are going to go. They're going to go 7, 8, 9, 20. But I wonder how we actually make 9 equal pieces. I have an idea. Do you want to play a new game? Let's play a new game. It's called Function Machines. The idea is this. One of you is going to think up a rule, a secret rule. Oh, it's going to be me. I want to do a secret rule. And you put numbers into my secret machine, and I'll tell you what comes out, and we'll see if you can figure out what my rule is. I'm going to draw the machine. What do you want this machine to look like?
A square.
A what?
A square.
A square, okay.
Square.
Here's the square. I'm actually going to make the square into a house, okay? And the house has a door, and it's got, I'm a terrible drawer, but it's got a chimney. What comes out of chimneys?
Smoke.
Smoke. And the numbers that you're going to put in go in the front door, and they come out as smoke. And, okay, I'm going to make a list. This is what you're going to put in. Watch. This is really very interesting, Nathan. Take a look. You're going to put numbers in, and I'm going to tell you what comes out. Who wants to put the first number in? Aaron. 10. We're going to put in 10. Out comes, things are happening inside the house. 10 is walking up the stairs. Something's happening in there. Out comes, 13. Lucia, put something in.
You're always adding 5.
Always adding 5. That might be it. Lucia, put
Always
something.
adding 3.
Always adding 3. So either I'm adding 5 or I'm adding 3. We better check with another number. Put something in.
100.
Good. 100 goes in. That's a big number. It's walking up the stairs. It's going past that window. It's going past that window. It's now up in the attic. Out comes 103.
3.
Jasper,
5.
put in 5. What's going to come out?
3. 7.
7 might come out. Any other guesses?
0.
0 might come out. 8 might come out. Any other guesses?
A million.
1,000,000 might come out.
So, 3.
3 might come out. That's an interesting guess.
900.
900?
938.
900.
That's
Okay. Oh, 900. I guess I should write it that way. Actually, what comes out is, it's one of these numbers. It is, oh, you're right, it's 8. What's my rule?
3. Add 3.
It's the add 3 machine. It turns out to be the add 3 machine. Who wants to make up a machine?
3.
Jasper, don't tell us the rule. Don't tell us the rule. What do you want it to look like? It can be anything you want. What? A square. Do you want it to look like an animal, maybe, or
A giraffe.
a giraffe? Good. Okay, I'm not a very good giraffe drawer, but I'll try. This is a very interesting giraffe.
This is the fun chapter.
And the numbers are going to come in right where the neck joins the body, and the numbers come out the giraffe's mouth. Okay. Now, Jasper, think to yourself of a rule which is going to take any number that goes in and do something to it. But don't tell us what it is, and we'll give you numbers. Samantha will give you a number, and Nathan will give you a number, and then you tell us what the machine does to the number, what comes out. We'll try to figure out your rule, okay?
Is good. And that's starting.
Nathan, what's happening here is this. Jasper has a giraffe machine, and numbers are going to go in. You're going to put a number in, and Jasper will tell us what comes out, and we'll try to figure out her rule, okay? Okay, are you ready? Do you have a rule?
5.
5 is going to go in.
No.
Can't put 5 in? I'd like it would be nice if it were a giraffe that could eat any number and then turn the number into something. Like, well, my rule was adding 3 to the number, and your rule can be something different from that.
That's okay.
Do you want to work with Samantha on this?
Are these guys evil?
Just together, make up a good rule.
Why is that guy
This is hard
That's
to understand what's in the giraffe's mind. 16 comes out? Huh. Okay, everybody, this is interesting. Nico, Aaron. When 5 goes into Jasper's giraffe, 16 comes out.
It's 11.
You think it's the add 11 machine. Ben thinks that this is the add 11 machine. Well, you can test that, Ben, by putting something in, predicting what's going to come out, and we'll see if you're right. Put something in.
3.
What do you think is going to come out? Don't tell us, Jasper. What do you think, Ben? You take 3, you add 11 to it. What do you get?
14.
14. Okay. You think 14 comes out. Jasper, what does come out when you put 3 into your machine?
4. 11.
11 comes out. Uh-huh. And is this the same rule that worked before? Or is it a different rule?
3.
Same rule. Okay. When the number 3 goes in, it gets chewed up and something happens to it and 11 comes out, right? May I put a number in? I'd like to put in 1. What comes out? How much? 1 comes out. I think this is a very interesting machine. Does anybody see what its rule is? I'm puzzled by it. Is it always working the same way?
No.
No, it's working differently. Jasper, tell us how your machine works.
Up.
What? Okay. This is kind of the I don't know machine. A number goes in and then another number comes out. I think that was a really good guess, Ben, from the first example, that it might be an adding 11 machine. And 11 and 3 is 14. That's good. Have you ever seen those scales? Maybe you have them at home, where you can weigh things. They look like this.
What's that?
It's one of those kitchen scales. You put weights on one side and things like potatoes or apples or something on the other until they balance. Ever seen those?
Yeah.
Have you ever seen one?
Yeah.
Reed, have you ever seen one? No? Samantha, have you?
I don't know what you're talking about.
I don't either. I was thinking of those scales where you want to balance things. You can put an apple on one side and then weights on the other to find out how much the apple weighs. But if you haven't seen one, let's not do that. And instead, Samantha, give me a number. Any old number.
0.
0 is a good number. Reed, give me a number.
1,010,000.
1,000,000?
1,010,000.
1,010,000. Okay. 0. And when you add to 0 something in this box, I'm going to give the box a name later, but right now I'm just going to call it box. When you add whatever is in that box to 0, you get 1,010,000. What's in the box?
4.
4, because 0 plus 4 might be 1,010,000, right?
No.
Why not then?
Because 0 means nothing.
Okay, so what should be in the box?
1,010,000.
1,000,010 is in the box. Okay. Actually, I think you're right, because when you add nothing to 1,010,000, you're going to get 1,010,000. Jasper, give me a new number. Any old number. 11. I'll just take the 11. 11 plus, Reed, give me a number. No, you give me the last one. Samantha, give me a number.
20.
20, good. 20 plus something in the box. 11 plus something in the box is 20. What's in the box?
9.
9 is in the box. Really? You're sure? Samantha, is that right? 11 and 9 make 20?
No.
No, what should it be? Here's 0. 1, 2, 3, 4, 5. Tell me if I'm doing this right. 6, 7, 8, 9. That's where we're we're standing at 11. We're standing here. And we want to get up to 13, 14, 15, 16, 17, 18, 19. We want to get up to 20. How many steps do you have to take from 11 to get to 20? Take a close look. Yeah, come on up. Start on the 11. You did it correctly, Ben. What did you get as a number? 9. Yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9. It was. 9 was hidden in the box. Why don't you make up one of these? Let's start with Ben. Give me a number.
0.
Too easy. Make it harder.
1010.
Too hard. Make it something in between.
200.
200. Okay. Samantha, 200 plus something in the box is going to add up to what? Make up a number. What's your favorite number? 4? 14. Okay. Have a seat again. Have a seat. Read. Now, look, this is interesting. I don't know if humans can do this. 200 and something in the box ends up giving you 14. Can you do this?
No,
Why not then?
because it's less than 200.
Because the 14 is less than 200. So what would be in the box would be pretty strange. Could I make it 15 plus what's in the box is 14?
No,
What do you think, Reed? Can we do this? Is there any way of figuring out what's in the box, if anything's in there?
no, no.
No, there's just nothing in there. Okay, I think you're probably right. All right, last question. I want to go back to data. We started with data, let's end with data. You've got the numbers going on like this. They keep going on. The dot, dot, dot means 5, 6, 7, or data. And finally you get to that very last number. But before you all go away, and before I go home, I want you to prove to me that that really is the last number, that there's nothing after it. Or prove that there is a number after it. Whatever it is, there's more. Samantha, you're right. There is more, but how do you know there's more? What makes you so sure that there's a number after data? Numbers never end. Here's a possible number after data. What about the number data plus...
Data is really a number.
It's really a number, it's just we don't know its actual name. We're just calling it that.
No, it's a word. Yeah,
It's a word. Well, 2...
No, it's a word.
Is it-
Dada.
Isn't 2 a word?
Yeah.
And 2 stands for that. And maybe data stands for...
Dada is a word.
Okay, I'll take a different one. How about the word... Oh, how about just box? I say that the numbers go 1, 2, 3, 4, and then they stop dead with whatever's in that box.
No.
Why not?
It's a word.
That's a picture.
No, it's a word. A box is a word.
A box is a word, you're right. Box is a word. Well, maybe this is a real puzzle. Maybe humans just can't figure this out. Maybe we don't know if there's a last number or not.
There is. I mean, there isn't.
Oh. Why isn't there?
Because numbers never end.
I think 10,000 is the last number.
No.
Give me one that's slightly bigger. Just slightly.
10,001.
Oh, you're saying whatever number I think is last, just add 1 to it and you get a bigger one. Even if that number's name was data. Data plus 1 is bigger than data. In your absence, lady and gentlemen, in your absence, we figured out that there's no last number because if there were a last number, you could add 1 to it.
There is a last number.
Well, infinity, is infinity a number?
No, Google is not a number.
Okay.
Google is
I leave you with this to think about. Is infinity a number? What we now know, Nathan, is thanks to the experts on my right, we now know that whatever last number you suggest, you can add 1 to it to get a bigger, but we don't know about infinity. Thanks a lot for helping me with all this. I won't have to think about it anymore. Questions? Answers? Neither or both. Yes.
How did that go for you?
It was fascinating, and what a nice question to ask. It went like this. Concentration went 3 or 4 times. The third time I thought, let's do function machines, which, because the notion of a rule was just so unfamiliar, didn't quite work. In one class I did at Harvard, a boy said he had a rule, he had a rule. We'd done several function machines by that point. And we put numbers into his machine and wild things came out. And finally we said, okay, what's your rule? His rule was no dogs allowed. Well, it is a rule.
The dog never came out.
Never. Dogs never went in. I thought that I didn't know that they were going to be as good as at doing all this as they were. When infinity came up, I regretted it because it threw us off stride about last number. To get the +1 from Ben at the very end was a real treat. And this always is a high wire act. You just don't know if it's going to work or not. What I'm hoping is that they go off and at some point in their lives, preferably in the next 6 weeks, they think about, is infinity a number or not? It's such a good candidate for being a number. You know that Euler had a different number system from ours. In Euler's number system, infinity is a number, which is why he can deal with divergent series in the way he does. There was a Russian mathematician, Yasenin Volpin, who in the 1960s, a constructivist, said 10 to the 10 to the 10 is infinity, i.e. it behaves like infinity to all intents and purposes because 10 to the 10 to the 10 plus 1 is basically 10 to the 10 to the 10. So why not treat it as if it were infinity? Just huge mysteries that are converging on this one point. Oh, 2 hands at once. I saw yours first. What, my program, or are you asking where they came from? I don't know. Sorry?
6 of them came from preschool.
Wonderful. They obviously have very good teachers.
Garden Day Preschool. Thank you. So, yeah, because their knowledge base seemed huge. Yeah. This is. And they were handpicked from that group of students.
Aha.
That group of children.
I see. We always actually prefer to have an utterly random sample because you never know who is a sleeper cell in there. Yes? Age 4 to 5? Yes. Pretty good, huh? Yes.
It's a word to them and it's a number to you, right?
Yes.
I was thinking,
Great question.
by just saying that, okay, 1, 2, 3, 4,
Right.
but they also have names. Not just English.
Yes. That,
I'm sure they're familiar with this number.
yes.
Maybe the students thought that name versus number.
And they're right, and they're at an age when words, when language, when naming is so important, and that clearly is something we got caught up on. Dada was such a dangerous choice for the name for the last number. A poet. It's the more general question: how much does one help or hinder? Ellen has a very good metaphor, which is that we're Sherpas. They do the climbing. We bring up the supplies. We point out, there's a crevice over there, better not go that way, or look, here are some steps. But try to do that as little as possible. Let them work it out themselves. It's going to take a long time, but it's better that way because it's theirs. They own it. They come away with, that's Ben's insight. That's Milo's infinity. And that way it becomes a part of their personalities. Whereas if I were to have said, gee, what if we try adding something to that possible last number? I've taken away from them the chance to discover it. One thing about the growth of knowledge in our math circle, at least, is exponential. It's very, very slow at the beginning because of the toing and froing, the back and forth. But it's amazing how it accelerates. With my 12 to 14-year-olds, the question I began this semester with was, if you've got a circle with an inscribed quadrilateral, and AB times CD plus, and at that point I stopped dead and said, what? And they said, well, it's got to be BC times AD. I said, okay, equals what? A short pause. And they said, well, it's got to be AC times BD. Fine, that took all 2 minutes. Then I said, why is this the Pythagorean theorem in a general form? And amazingly quickly, someone said, well, if that were a rectangle instead of an arbitrary quadrilateral, you'd get a squared plus b squared equals c squared. Terrific. Then I said, okay, prove it. And we stopped dead in the water. Ptolemy's proof, this is Ptolemy's theorem, is extremely subtle. He draws one line which one just wouldn't come up with. So I said, well, why don't we just give this up? We talked about it for half an hour, couldn't see a proof, and sailed into inversive geometry, which we did for the next 6 classes, developing this geometry where the one relation is that if you have a circular mirror, S, with center A and radius R, any point gets reflected to another point, its mirror image, by the rule that AZ times AZ prime equals R squared. It's the only rule of this geometry. And from it, you develop very beautiful geometry where points inside the circle go to points outside and vice versa. The point A goes to infinity. It's the one point at infinity in this geometry. And all of a sudden, after 6 weeks, Ptolemy's theorem, the proof of it, falls out of this. Because circles going through the center of the circle of reflection get mapped to straight lines. And so the awkward relation between the vertices of a cyclic quadrilateral get turned into points on a line segment, and it's very easy. And because it took a long time to start and a long ups and downs along the way, when they got it, they knew that they had gotten it. They'd forgotten I was there. I was just their secretary. And they went home elated and exhausted. How much better than to have said to them, well, let me show you this proof. It's really nifty. Other questions or comments? Yes?
As the time went by and you saw that some of the children, and right before they left, you talked about having this function machine, let's play this in out. Was your intention at that moment to come back to it at the very end and think of +1
Yes.
and get that from them?
Yes. The eyes had glazed. I thought, let's just drop this entirely, do function machines, let things relax, let them subside into the pre-un or subconscious, and then come back to it. It's too bad they left because I think certainly Nathan and maybe Milo and Lucia, who had really good ideas. It was Lucia who saw how to cut up the cake. You notice the number of leads that I didn't follow that I wish I had, getting fractions by cutting up that cake into smaller bits. So,
Somebody said after we counted the slices on the cake, X out the 8, which I found fascinating. Did you hear that?
what was the remark? What, 8?
You were Xing
Yes.
out, crossing out 5 and 6.
Yes.
It couldn't be 5, couldn't
Right.
be 6. We counted up 8 labels.
Yes. Yes.
And somebody said X out the 8.
I didn't know what that meant. I guess I couldn't believe my
Cross it
ears.
off because it's wrong.
Because it was
I
wrong.
thought-
I'm almost sure that I'm telepathic, so I know that what they were actually thinking was every time you got to a number, they didn't realize every time you passed a number. but
Right,
every
right.
time you got to a number,
Right.
you crossed it out.
So it didn't mean that's wrong. It just meant
That we've gotten to
you get
that.
to it, X it.
I think that's what she was thinking.
Maybe.
So then it was good not
Be-
to follow it up.
Well, I should have been more alert to that crossing out. It was interesting that they wanted 9. Often what you want superimposes itself on what you've got, in one's own mathematical work. You say, of course I've got the proof there, I just will ignore this thing over here. Maria?
At first, and links active.
Yes,
And think how the most staying power is stable and concentrated
yes,
a lot.
yes.
How that is.
Fascinating, isn't it? You just never know.
And you assume that they were not marched in any order. They ordered themselves once they were in the chairs.
But it's even interesting they weren't participating much at
Yeah, yeah. I was doing a Cantorian set theory class with 9 and 10-year-olds once, and it was going beautifully until we got to the fact that there is no, you can't have a set containing all sets. And the proof is difficult because you're looking at things in a twisted way. There was one girl who had been there through the entire first 7 weeks, hadn't said a word, except when naming came up. She was good on looking for names for things. And I thought, well, she's here for the ride, but the time will come, who knows, in a couple of years when all this will mean something to her. And we were stuck on what to do with power sets. And she said, well, you just, and unrolled the proof. And the boy sitting on her left turned to her and said, what? And she said, what? He said, but you haven't been here. She said, I've been here the whole time. And he said, but we've been doing this for 7 weeks. You haven't said anything. She said, we've been doing this? It's weird. Kids are weird. We are weird. You just never know. Let things ride. Yes.
I have 3 comments now, and I'll try to make them brief. I love the way that you kind of homed in on the mysteries of, well, first you described doing that for area, and then when the kids came, of numbers and things like that. I love the way that you just homed in on the mysteries and let the kids figure it out
Yeah.
to the extent they could. also think, well, I was going to mention the same thing someone up there did, that the question of dot as a name for a number is really a tricky conceptual idea, the idea of X for an unknown. You know, it
Yeah.
opens a whole field of algebra, and that's, I just want to emphasize that I think that's a pretty tricky
Yeah.
thing to get past. And lastly, I don't know why the kids on this side were less active at the beginning, but I think at least 3 of the kids on that side nearest the wall.
Nico,
Yeah,
Nathan.
whoever were the 3 nearest the wall
Yep.
had a little trouble seeing the board.
Oh, you're probably right.
And that
Yeah.
that might have had something to do
No,
with
it's a
their
very good
being
point.
restless.
A math circle should be a circle so they can see one another, but then where on earth do you stand at the point that gets sent to infinity?
Well, we didn't need the space for us to see.
Yeah, yeah, quite right. I had a covert plan in mind with the box thing. I was going to go, had I had more time, I would have, from box drawn like that to box written saying, I just draw such terrible pictures, do you mind if I use the word? And finally saying, look, I just don't have time to write all that. Can I just write X for box? But that would be after several classes. And I think this issue of names, of naming, is a really crucial one. And I would love to have more suggestions about how to handle it. How are we doing for time? Are we running out? Or? Good. We have run. Then I saw your hand.
Well, I just thought it was interesting that, as a discussion just now, that we went to these kids, it's strange that they randomly sat there even though they were the quiet ones, when in fact, it probably was random. It's more of a group dynamic thing, and that's, anytime you're in a classroom, 2 different classroom settings with the same kids, like you rearrange, you get totally different
Quite right.
responses.
I think Ben had a radiative effect over here. And Nathan did over here in both benign and malign ways as the time went on. Thanks very much, everyone.